Hi, everyone, and thank you for joining our today's QED-C Quantum Talent Showcase session. My name is Reza Hedayati, and I'm the new coordinator of the Quantum Talent Showcase moving forward. I will do my best to take over the great work of Mr. Adrian German, who has done a fantastic job organizing and moderating these sessions over the past 3.5 years. Thank you, Adrian, for all your hard work. After a brief introduction of these sessions and the presenters, I will hand it over to Mr. Alan Pierre Louis, who will be moderating the Q&A sessions, the portions of the presentations. First, a brief statement about these sessions. These are called Quantum Talent Showcases, a bi-monthly series of presentations from quantum student and postdoc researchers at top universities. And it's organized by QED-C's Workforce Technical Advisory Committee. These sessions, just to make a note, usually happen on the second Tuesday of every other month, but today is an exception. We're holding it on a Monday, but they're all scheduled on Tuesday, the second Tuesday of every other month at 3 p.m. Eastern. This is a public event and is a great place for the presenters to have an opportunity to connect with industry organizations and also for the industry organizations to find elite quantum talent entering the workforce. Our first presenter is Ms. LaToya Anderson, who is an associate research analyst in the Center for Computational Quantum Physics at the Simons Foundation. She's also an undergraduate at Brooklyn College's City University of New York, a Team Up Together scholar, and the 2022 NSB Best Student Oral Presentation Award winner. Her research is focused on the application and development of computational first principle methods over novel 2D quantum materials. Our second presenter is Mr. Cornelius Salonis, who is a senior at Alabama A&M University, majoring in physics. His college journey incorporates diverse internships, such as the National Defense Education Program and REU at Indiana University in collaboration with Oak Ridge and Los Alamos National Laboratories, as an IBM HBCU quantum research scholar and Inspire researcher. His research spans topics like diproton emission from heavier isotopes, utilizing multi-layer perceptrons for density functional theory, and analyzing silicon photomultipliers for use in the UCN tau experiment. He has presented at notable conferences, won positions in a think tank competition, and served as the president of the AAMU Chess Club. Recently, he co-published a theoretical research paper after completing a summer research internship at the Simons Foundation. Constantly pushing boundaries, Cornelius strives for personal growth, recognizing that leadership is about guiding his own life. Thank you, and go ahead, LaToya. Can you stop the share?
Just wanted to give a slight preamble to that before we start.
Sure.
So thank you everyone for attending. I just wanted to highlight the National Society of Black Physicists, which was founded in 1977 and supports students of all backgrounds and highlights Black physicists and their advances in the field. And there will be another conference similar to the National Society of Black Physicists, or NSBP, happening from June 12th to 14th at Harvard, called Quantum Noir, which will have presentations like this one that will highlight Black physicists specifically in quantum physics. So without further ado, I'd like to allow LaToya Anderson to go with her presentation, and thank you, and please give her your full attention.
Well, first, I want to express my thanks to both Alan and Reza and the rest of the QED team for inviting me to give this presentation today regarding my research. Let me start sharing my screen and to share all the work that I've been doing at the Flatiron Institute. So what I'm going to give my talk on today is localized superatomic Wannier functions for superatomic solids. And this is research, as I shared, that I've been completing at the Flatiron Institute. And my hope is that by the end of the presentation, everyone will not only have a sense of the potential usage of superatomic Wannier functions, but are actually excited about quantum materials, in particular, superatomic solids. So in order to even delve into those topics, we do have to take a step back into the beginning, where I will give a very brief introduction into density functional theory. I'll then transition into maximally localized Wannier functions and how they are used in the type binding model in order to gain additional insights into quantum materials. Then from there, I will talk about what superatomic solids even are, and then why they are an exciting new area of research within quantum materials, both theoretically and experimentally. And then finally, of course, actually delve into what superatomic Wannier functions even are in the first place and their potential usage in both theoretical and experimental quantum materials. So to begin with any quantum system, we do have to begin with the Schrodinger equation. And the Schrodinger equation is what is used to gain information and predict behavior of quantum materials. And so as you see in this equation, this, for example, is what's called the time-independent Schrodinger equation. And what we do is we solve for the wave function, and that wave function is the psi Greek letter that you see in this equation. And by solving for that, we can actually gain information regarding our quantum system. Once we solve for that equation, the main thing or the main issue with solving this equation is that we can only solve it exactly for up to a hydrogen atom. Once we move into more complicated systems, that's when it becomes computationally intractable. And so we need additional methods in order to... Oh, does someone have a question? Oh, okay. I think someone just unmuted themselves by accident. So in order to solve the Schrodinger equation for many body systems, we do need to introduce new methods. And so the method that is used most often within the quantum materials community is density functional theory. So this is a method that's used to approximate the wave equation for many body quantum systems. And if we take a look at the image that we see here, where we see an ion with many electrons and mapped as that many body problem. And you'll see that there is a transition over into the electron density. What this beautiful picture is showing is what is occurring mathematically in order to simplify this problem to allow us to solve it, at least for approximately. So you'll notice that there are interactions. For the ion, that represents the protons in our atom. And there are Coulomb interactions both between the ion and the electrons, as well as between the electrons themselves. So there are a lot of interactions, and the combination of those interactions, plus the quantum mechanics quantum mechanical properties that makes this problem complicated, they have simplified this problem, so we only focus on the electron density. Once that problem has been mapped to an electron density problem, we can then calculate what's called the Kohn-Sham orbital energies, and therefore plot the band structures or the electronic structure of this material. Once we calculate those Kohn-Sham energies, we create what's called a block function or many block functions. And that equation is represented on the side of your screen under the graphic that says block functions. And pictorially, that's what you're seeing in the photo here. What that block function is doing is showing the fact that while we are solving the Schrodinger equation approximately for said atom, if those atoms are in a quantum material, that material is what's called periodic. meaning that there are many atoms that are stuck together or covalently bonded together. They have the repeating same structure. So we can map, this is how we represent that mathematically and pictorially. However, there are limitations to density functional theory. A couple of them being that when we are trying to discover properties of the material, one of those properties is called a band gap. And that is the distance between the valence bands and the conduction bands. So the reason that's important is that tells us whether or not we have a metal, an insulator, or a semiconductor. So we need to refine that calculation. In addition to that, if we want to gain additional insights, such as the chemical bonding features, that's when we need to have maximally localized Wannier functions. And so to give a really good picture of what's occurring, we're taking a periodic function represented by these block functions in this picture, and then we are performing a unitary transformation so that once we perform the unitary transformation, we're able to recover the molecular orbital information. And that's beautifully shown in this bottom photo here. So this is gallium arsenic. And what you're seeing here for the bottom bands within this band structure, this represents the s orbital or the s band. And when we perform the Wannierization of this material, we recover the s orbital. And above there, we have these three bands above there. Those are the p, x, p, y, p, z. And when we perform the Wannierization of said material, we then recover the p orbitals. Now, that's great for specific atoms or materials composed of atoms, but the material that I am studying is what's called superatoms, which then form superatomic solids. So there's still a bit of a limitation to the information that we need. So now you might be wondering, well, what is all this talk about superatoms? So superatoms are discrete molecular clusters that exhibit atom-like properties. For example, in the superatom that I study, it exhibits similar properties to sheets of silicon. And why could this be an exciting area of research? The reason it's exciting is that because we are dealing with multiple atoms that are, for example, covalently bonded together, they exhibit properties of those the atoms that we typically use in our electronics. However, now we have a recipe. We can actually tune these superatoms to specific properties that we may need, magnetic, optical, as well as electronic. And that creates exciting opportunities in materials design. So this is where we step into superatomic solids. So superatomic solids, as you might have guessed, they are composed of superatoms that form these two-dimensional sheets, and that's what you see on the picture to the side of the frame. That is a two-dimensional sheet of the system that I study, and you're taking a top-down view. These are covalently bonded together, and then if you want to form a three-dimensional bulk structure, you stack them one on top of one another, and in between, the interaction between those stacks is a van der Waals interaction. So why this system in particular, which is rhenium selenium chloride? It's a superatom that forms these superatomic solids, and they are composed of 6 rheniums, 8 seleniums, and 2 chlorides. Or for one, it is a room temperature semiconductor that's formed by superatoms, and their structure is a triclinic lattice structure. As I showed before, once these superatoms are bonded together, they form those strong intercluster covalent bonds to form those two-dimensional sheets. Those van der Waals interactions, once you stack them one on top of another, that makes it easy for mechanical exfoliation and stability under ambient temperatures. Now, why this material in particular? I mentioned before that it does have similar properties to silicon, which is used in our electronics. However, there is interest due to its energy transport features. So far, there has been preliminary research that shows that it is capable of having scatter-free free flow at room temperature when this material is excited, unlike sheets of silicon, where when phonons are released due to the vibrations of those quantum particles that within the quantum material, those phonons end up scattering and ricocheting off the other atoms. And that ricocheting makes them lose energy. And we want to maintain that energy to gain as much energy from that system. In addition to that, there are superconductor features, mainly being that once heavily doped, it exhibits those superconductivity properties at about 8 Kelvin. So still at low temperatures, but obviously slightly higher than what we've currently found. So I mentioned a little bit earlier that the first step in studying a material is applying density functional theory. So I applied density functional theory to my super atom and calculated its band structure, which is what you see on this slide here. To give a sense for anyone who's not familiar with band structures, basically what you're seeing is a plot of energy where if you were to take this super atom, label all the different parts of this super atom with these letters, which is what you see on the bottom, and trace through the entire super atom and measure its energy, this is what you would come up with. And keep in mind too, that these are super atoms that of course have electrons, so we're measuring the energy of those electrons. So the thing to notice about this is if you're familiar with band structures, they typically have very high peaks and very low troughs. But here, the bands are pretty flat, and that suggests strong electron coupling, or another way of saying that is that the electrons like to pretty much stay put within their respective superatoms. Or at least if they are going to move, they move to their nearest neighbors. Rhenium ends up actually having the largest contribution of projected density of states, and that's what you see when, if you look at the plot next to the band structure, and that green section there, that's the rhenium atoms. So keep that in mind because this upper section here are the conduction bands, which means that those are the potential locations that electrons will jump to when this material is excited. So now this is where superatomic Wannier functions really shines. So I've gained information in terms of its electronic structure, but I still don't have a chemical sense of what is occurring with the superatom. So the feature with this superatom is that while these electrons are strongly coupled to those superatoms, their orbitals actually delocalize from the atoms themselves and relocalize across the entire superatom. And so we need a picture of what's actually happening. So this is where superatomic functions occur. And the picture you're seeing here, if you look where it looks like there's lots of bubbles, those are the potential locations that electrons could jump to when this material is excited. And this is due to not only the fact that this is a superatom and there are different orbital features within the superatom, once covalently bonded with its respective superatoms, there are also interactions between those atoms themselves. So this model could potentially provide a chemical intuition into those superatoms in terms of their supercluster interactions. Now, not only have we gained that intuition, it also brings us to a new starting point to gain additional information, where we can extend this model to applying dynamical mean feed theory for these calculations, to build a Hubbard model in order to probe for additional properties, such as those phonon interactions that I mentioned earlier. And so next steps are to apply the same model to another type of superatomic solid called graphularine. And graphularines are buckyballs or the fullerenes that are covalently bonded to one another. That's what you see in the top view section of the picture. And then again, one stacked one on top of one another on the side view, they have those van der Waals interactions, and seeing what information we can gain from there. And then of course, submit for publication and all that good stuff. And so finally, I do want to thank my mentor and principal investigator, Dr. Tim Berkelback, because we have been working together on this project. during my time at Flatiron Institute, in addition to his graduate student, Petra, who's also been contributing research more so on the Flatiron side. In addition to that, the scientists at the Flatiron Institute, namely Dr. Cyrus Dreyer, who, as well as Sophie Beck, who both have been helping me with honestly learning how to use all the software that's needed to study this material. And then finally, the Flatiron Institute for supporting my research interests and for their partnership with the National Society of Black Physicists. And so with that, here are my references, and I want to thank everyone for listening to my research on superatomic solids.
Thank you so much for that, LaToya. Right now, there are questions that can be put in the chat, or we can have people volunteer to have a voice chat to connect to voice chat and voice their questions. But thank you for that excellent talk. Very enlightening.
Absolutely.
And if there aren't any questions to start, I might pose one just to get the ball rolling. So you mentioned mechanical exfoliation. Could you go over again why the weak van der Waals forces allow for that, and what is mechanical exfoliation again?
Oh, sure. So van der Waals interactions are a type of interactions between two different types of materials. So we actually do experience van der Waals interactions almost every day. One example is if you were to pour a glass of water, and of course, you're going to see water droplets on the side of your glass. So the reason that the water sticks to the side of the glass, part of that is due to van der Waals interactions. And so as that water travels or trickles down that glass towards the main section of your water, and you'll notice that trail of water rather than the entire mass traveling down, again, that's due to van der Waals interactions. So the reason that's important in terms of exfoliation is that with superatomic solids, there are emergent properties that occur between the two-dimensional structure versus the three-dimensional bulk structure. So if you have a three-dimensional structure and you want to examine those properties, they are going to be slightly different. That's part of the tuning that would happen compared to a two-dimensional structure. In terms of what mechanical exfoliation is, it depends on the material, but I mean, I'm not an experimentalist, but I think one way is you can, like a way to think about it is if you were to, let's say, shine like a table. So you have this table that has a whole bunch of stuff on top and you want to get to the shine of the wood itself. Get sandpaper and you shine it down. That's what's happening. You're removing layers with whatever techniques that they use in order to get to that 2D structure.
All right, thanks so much for that explanation. Very fluid. So we have a question from Ibrahim here in the chat, and he asks, what applications is the study aiming to be used for, such as in industry?
Sure. So so thank you for the question, Ibrahim, and I see the 1+ for Erin. So the main applications are in particular for nanoelectronics, as well as potential uses in quantum computing. So while these types of materials are still at the very beginning stages, but what makes them special is the fact that now we have a recipe of atoms that we can work with to tune for properties that are needed for those types of electronics. So say, for example, with quantum computing, one of the issues in terms of quantum materials is finding quantum materials that can be used at room temperature but still maintains all of those quantum features that we love so much in order to make our calculations. There is potential for superatomic solids to be tuned so that even if it's not necessarily at room temperature, if at least it's above the current temperatures that are currently used, we've now made additional leaps in research to scaling quantum computers. So that's one potential area.
Okay, thanks for that. I don't know if Aaron had a question or if that was just
I just really like Ibrahim right now because he keeps asking the questions I want to ask. So
okay, great.
Love it when that happens.
For sure, for sure. So I'll read his next. I think there's another question from Ibrahim. So thank you. That's great to hear. What is the next couple of phases / projects of your work you're looking to execute?
Sure. So the next step is to not only apply this method to other materials such as graphullerene, but to also make additional refinements to these superatomic functions. So this is preliminary research, and we were able, me and my mentor, were able to recover the molecular orbitals that are due to the fact that it is a superatom in the LUMO section, and I did not mention that before. So LUMO is the lowest unoccupied molecular orbital. So referring back to the band structure here, so this band structure, the overall goal, if you're not familiar with band structures, is to get a sense of how the electrons are spread not only across the material, but also potential locations that the electrons can hop to once excited. So the orbitals, the pretty colors that you saw before that look like balls, that is representing the spaghetti plots that are above the 1 eV. And that's what you're seeing in this band structure. So that's great. We want that information, but we also want information that's along the valence bands. So that's where the EV starts at 0 and goes and drops down. So that's also the next step as well, to recovering that information. And then from there, publishing, graduating from school, getting a job, going to PhD program, all that good stuff for physics.
For sure. Good luck with all that. Okay, we have one more question, and then I think so we will exhaust the 30 minutes, so we'll head to Cornelius after this question. So
Sure.
is there, and this is from Ibrahim as well, is there any consideration for linking superatomic research with the extractions in optically levitated nanoparticles?
There is. It's outside of my field, but there is. So there are people, I actually know a couple of other graduate students within my mentor's group. They focus more on that side of research. And so that is what they actually study. And I do know of a few researchers at NYU who are also doing the same. They may not be focusing on super atoms, but they are interested in novel materials, and they focus on that type of research, which once introduced, because there is research in super atoms at NYU, that will hopefully gain underway.
Okay, thanks so much for that, LaToya. So yeah, we'll give you a virtual hand, and that was a great presentation. Thank you for representing your institution so well. And now, without further ado, we'll get into Cornelius Salonis and his presentation. We are eager to hear it, and please give him your attention.
Hello, everyone. So I'm Cornelius Salonis, a rising senior at Alabama A&M. And today I will be giving a presentation on my quantum journey. So what I describe my quantum journey is my beginning from freshman year, really actually high school, until now. And it tells the story of my journey and how I came to be where I am today. Good. So going in, I want to give you guys a little timeline about who I am, leaving high school, what got me eager to be a physicist, how it all began, kind of background information about myself. After that, I go into my spill about from alpha to omega, starting my freshman year as a physicist, my sophomore year, junior year, the internships I was a part of, presentations I've done, the research I've been a part of, many side projects. And then from that, going kind of today, where I'm at today, what am I looking to do going forward, and the aspirations I have. And then after that, going into questions. And before I kind of get into my talk, I do want to also give a thank you to everyone that kind of helped contribute to who I am. Thank you, Alan, for inviting me. Thank you, LaToya, too. I spent the summer with LaToya, so she's also an integral part about who I am and how I got to this position I am today. So for everyone in the physics community that has been a part of my life, thank you so much. And then let's get into our presentation. So starting from the basics, I was born February 16th, 2002, raised in Shakopee, Minnesota, then moved to Minneapolis around 2010 after my father passed away. And since a kid, I've always considered myself a science kid. I never really see myself doing anything outside of science. Some people gravitated towards athletics, towards arts and crafts, engineering. Me, myself, I was always a science kid. And I love watching science channels. I love watching shows that help me understand what the universe was. What is this big planet of rock and sand and dirt that I'm living on? Those are kind of questions I asked myself as a young kid, and it has helped me propel myself into this regime. So up to this point, so after leaving high school, I was a part of some different opportunities. I was a part of my local BSM engineering club where we participated in a RoboCup. I helped make the camera systems, the steering systems, so that we can monitor the robot throughout the track. I volunteer for MN STEM Partners, which is an inner city program that helps to bring robotics to underprivileged kids. I had 2-year experience at my local grocery store. Only job I had at that point. Had a 2.8 GPA and a 28 ACT. And I share this because for me, leaving high school, I always thought to myself that I wouldn't have any opportunities to be able to engage in the scientific community or internships, research, or any robotic clubs I wanted to do. But I came to find out sooner than later that that was not the case. And actually in the ACT, science was my lowest score. So after taking the ACT, I took it twice. Both times, science came out to be my lowest subject. And I add this because that also just adds another layer to my story that I think is very important. That, at the time, even as much as I love science and physics, I was still scoring low. But to this day, I still stuck with the subject. And I think that's an important aspect about being a scientist or doing what you love. And then I also was a part of a Discover STEM program, which is a local program that was hosted at the University of Minnesota, and which it just helped to expose us to more scientific research. So this is my resume up to that point. Not much to it, just kind of bare bones, just sharing my experiences up to that point. So leaving high school, this is my resume. Not too much to it, not much going on, but I have a resume nevertheless. Okay, and so in high school, some of the subjects that really helped kind of put me where I am today is math, chemistry, and physics. And so I have the arrows pointing to each other just to show how the correlation between each other. So in in math, some of the most important skill sets that I learned is a standard order of processing or operations. So being able to understand that there is a order to things, that I can't just do things in an arbitrary order and expect the same results or expect a correct answer, that I need to follow a step-by-step order of process to get to the answer I want. Analytical processing kind of goes along with that, just going analytically, thinking through step by step. And then a mathematical foundation, just understanding cosines, trigonometry, geometry, all the important mathematical foundations you need. And so from math, I took chemistry. In chemistry class, I think this is another one of the most important classes I could have taken in my career, because from math to chemistry, in chemistry, I was able to learn how to conceptualize non-analytical systems and problems. So chemistry does a lot of molecular bonding, atomic structures, and that's not very easy to visualize. And so I was able to learn how to visualize better in this class. And from chemistry, I took physics, and physics is kind of where I bloomed and blossomed into who I am today. Really, nothing needs to be said about physics. Physics is kind of everything. What we see is integral into everything we do. And so this helped me build a kind of idea of what I wanted to do going into college. And so this is kind of where I believe my trilogy comes from. So I believe that in language, the language of STEM has a language. So for me, the word is one of the most important fundamental parts of language and communication, because it houses meaning. Each word houses a meaning to be shared and communicated with. From the word, I relate this to math. And I say this because math is the foundational building block of all of STEM, of all of math. You can find it anywhere in STEM: engineering, physics, chemistry. So if you say math is the word, okay, then what's the next step from the word? A sentence. So the sentence, the astute nature of a sentence leaves the broader narrative ambiguous, leaves the broader story ambiguous. We have a lot of pondering to go through. And for me, I relate this to physics because physics tells us a story, but it doesn't give us the broader picture. There's equations that we understand can be used in certain situations. We don't know how to kind of at this point build them together. And so the culmination of the trilogy is a book. So from words to sentences to a book, the book completes the whole story. It tells us everything we need to understand to be able to share our experiences and share information. And I relate this to engineering. Engineering combines all three of the aspects of STEM together: math, physics, and engineering, to be able to produce the marvels and wonders we see today. And so that's important for me because going into college, that's kind of the mindset and belief I've had and outlook I had towards the sciences. And so kind of going into my freshman year of college, I wanted to be able to describe it in a quirky way in Dirac notation. We kind of get into that a little bit later. So start of the year, this is some pictures of me. And I believe that a photo tells 1,000 words. And so these are just kind of some photos about me freshman year, kind of starting my college journey, things that I was going through. My uncle is on the left, some math, beautiful photo of the skyline living on the hill at Alabama A&M, and then of my home, of me capturing thunderstrike. And so, starting out as a freshman in college, one of the most important parts for me was simply just COVID. Going from, leaving high school with the COVID pandemic in full swing, it really changed the way I interacted with my college professors and my physics professors. A lot of things was online and a lot of things were kind of closed off to me initially. And so I would say it changed my mentality in which I view physics, because I was like, okay, I'm closed off. It's just me versus everyone else. And it really did kind of change certain aspects about myself. So nothing too much happened importantly freshman year. Kind of COVID went on, things kind of happened, but towards the second semester is when my career kind of really began in physics, I would say. So during the second semester, this is when I got my first internship. So the internship I was a part of was called the National Defense Education Program. So and with this program, what it essentially is, it introduces freshmen, sophomores, juniors, and seniors, or most importantly, freshmen and sophomores, to their first internship program. So the way they do this is they focus on introducing freshmen and sophomores to the Department of Defense priority list. So there's certain priority aspects in scientific research that the Department of Defense is investing in. And so for me, what did I do? I was a part of the hypersonics propulsion team. So that just incorporated me and my team project to understand what hypersonic propulsion is, different propulsion methods, and just ways that the Department of Defense could utilize it going forward. What did I learn from this program? This is my first internship program, so it was a novel experience for me in which I was understanding how does top, educators and organizations look to utilize the research that's being done by scientists like myself. And so, as I said before, freshman year, nothing too extravagant happened. So by the end of the year, I had ended my year as a freshman. I had a summer internship with the National Defense Education Program, and I made the Dean's Honor Roll. So moving into my sophomore year, this is when things are starting to pick up for myself. As I said before, throughout the whole way through, I'm really ambitious. My whole goal freshman year was to meet as many people as I can and connect myself with the relevant people so that I can start putting myself in positions to leveraging my interests and conducting more specific research. So as I said before, by the start of the year, that's my goal. I want to be involved in research. I want to be able to expand my horizons and see what's available to me. And it's actually a kind of an inverse from what I was learning about leaving through high school, because I was told that not a lot of internship opportunities would be available for freshmen and sophomores, but already as a freshman, I was getting that opportunities I was told to me I would get later on. So that also just kind of helped develop my mindset to understand that science and physics is what I can do, not only what I want to do, but I can do if there's space and opportunities available for me. So getting into my second research opportunity. So when I come back sophomore year, that first semester, as I said, I positioned myself into the right places I needed to be, and I was able to get an internship opportunity. So I became an inspired student researcher, mentored by my professor, Tianxi Zhang. As I said, this is my second internship. And so what this internship focuses on is understanding within stellar objects such as the sun, understanding how diprotons can, the decay probabilities within heavier isotopes within the star, within the star. So we look at, this is important because within stellar objects, there's two main processes that fuel the star. So there's the proton-proton chain reaction, in which you can see there's three paths that the proton-proton chain reaction can take. We have the first phase, second phase, and third phase, and they all work by combining protons in a various amount of manners to produce heavier elements. So the thing with the proton-proton chain reaction is that the heaviest element that can form is beryllium-6. After that, the CNO, carbon, nitrogen, oxygen cycle takes over. And essentially with this research, I was just kind of focusing on how does, in heavier isotopes, the tunneling probabilities for diprotons. And this is important because there is a discrepancy between the calculated and the emitted luminosity of the sun. And so the proton probabilities, decay probabilities could be a solution. By understanding more how they emit within stellar objects, we can kind of reduce the leeway between the two. So kind of going from my inspired research opportunity, I had that for the first 2 semesters. I kind of continue on my track as being a physics student, taking my courses and everything. And by the end of the year, I get another internship opportunity working with Indiana University. I have an RU experience there. As I said before, a photo to me tells 1,000 words. And so this, in a nutshell, is my summer at Indiana University. So at the top, we just kind of have the overview schematic of what the Los Alamos National Laboratory experiment was conducting. The UCN Tower experiment, the goal with that is to essentially be able to measure the mean lifetime of a free neutron. So if you look at the top left schematic, that's the schematic for the Los Alamos UCN Tower experiment. Essentially what's happening is they use a spallation device to kind of free neutrons from isotopes. The free neutrons then go through this schematic, through the polarizing magnet, buffer volume, the spin flipper, and eventually ends up in the Halbach array. So this is kind of the main focus of this internship experience, the Halbach array. So to the left of that, in the middle, is a dagger array. So the Halbach array and the dagger system kind of work in tangent. The idea behind this is once the neutrons get within the Halbach array, that they are kind of suspended in space by magnets that prevent them from interacting with anything, any of the surfaces within the array. Once they are in the array, they get lowered down. The dagger array gets lowered down, and using a scintillator, anytime a neutron interacts with the scintillator, we get a scintillating event. We get a pulse of light within that volume. And then at the top, those blue lines are the scintillating events that's being picked up by fiber optics and being read out to a photomultiplier. And so at the bottom, though, the bottom 3 photos are kind of photos of what I was doing, working with the silicon photomultiplier. I end up having to create from scratch the dark box, which you can see on the bottom right. That dark box is basically a pseudo Halbach array in which we just have an LED pulsing, and that gets picked up by the SIPM. So everything at the bottom is all the work I had to do, kind of first setting up the experimental design to even produce data. So after I set up my experimental design, I went on to kind of reading out the data. So each peak you can see in the top, or all of these images, are kind of a representative of a scintillating event. So after I was produced the experimental setup, I then had to find a way to analyze the data that was coming through. So at the top left, we just have a basic bare bone photo of a scintillating event of the photo multiplier picking up detection events. After that stage, I then went on, okay, we had to get the events at different temperature ranges. So on the right, it's just at a lower temperature range. And then the next build up. So after that, I then had to set a trigger value to depict at what points do we want to start looking for peaks. At the bottom right, we have a better depiction of like the next stage in my research internship. I then, after finding a way to make a trigger value, which is the green line, I then had to make it so that it reliably picks out the peaks in the waveforms. As you can see, it picks out the peaks in the waveforms. After it does that, it then histograms the data so that we can start to understand, okay, are we getting the right statistics that we were looking for? On the right is just an example of me trying to reduce the noise, because during some of the setup, we had to change some things around, and that was when some of the noise started to become an issue. So at the top in the blue is the waveform with the noise. The red is the standardized without like the previous setup, and then the red at the bottom is the subtracted waveform data. And so by the end of this, we produce these graphs kind of just depicting wave amplitudes, the area under each specific peak. And then this is the progression of me fine tuning that these different graphs to be able to convey reliably the information. So by the end, on the far right is kind of the end result, what I have. So as you can see, the amplitude. So the farther you go, it's on the y-axis is the count, so the amount of the count, and then the x-axis is the magnitude. So for the first one, it's the amplitude, and then the second two at the bottom is just examples of the area under the peak, so that we can match it to the right photo spectrum we want. So kind of a big year for me. Sophomore year, I experienced my first two real internship opportunities. As I said, I had a summer intern with Indiana University. I was an inspired student researcher. That's also when I got my job as working with the physics department, kind of helping out with any labs, cleaning rooms up, doing any extra work that they needed me. And this just kind of came from me and being involved in my physics department. From my sophomore year to my junior year, this is kind of, once again, another big leap for me. This is kind of when I started to understand the path and layout I want my future to look as. So by the start of the year, my sophomore year, I've done presentations for each one of those internship opportunities I had. I presented about 2 or 3 times at different research presentations. And so at this point, I'm starting to feel that, like, okay, I can be a physicist, of understanding what it takes, the requirement it takes to be a collaborator in the field and to contribute within the field. And so I'm just taking that mindset going forward and just trying to push the boundaries more within my junior year. And so this is when I get one of my most important, I think this is one of my most important research opportunities, working with the IBM HBCU Quantum Center. So this opportunity arose from my inspired mentor, Tianxi Zhang, working on Josephine junctions. From the opportunity, he asked me, do I want to collaborate with him and work on the quantum HBCU Quantum Center? And so this, with this internship opportunity, the main idea is that they want to foster, teach, and support a new generation of HBCU students within the quantum information science and information. This is a new field that is revolving around quantum information, quantum computing, and anything related. And so with this internship opportunity, I kind of found it to be important because unlike my other ones in which I had a direct mentor, I was being taught things, on a hands-on basis. This one was kind of more so I am the driving force behind it, without anyone kind of telling me what do I need to do to excel myself. I needed to find a method to excel within the field myself. And for me, that looked like engaging within the quantum lab that IBM offers for the participants of this program, kind of reaching out to other people involved in quantum information sciences and getting tips from them, watching videos, doing independent research, and learning. And to this day, I'm still actively engaged and kind of continue to build my knowledge within the quantum information science because of the relevancy I see it and the direction I want to take my life. And so this is kind of one of my more harder internships because of the breadth of the research. And so I'm always actively looking for people to help give me tips, advice, ways to kind of take this so I can be adequate within the field going forward. But leaving, so as kind of continue through my junior year of high school, well, of college, I go into the summer with the NSBP Simon Scholar. And this one is, once again, I think all of them have taught me important lessons, but this one just once again helped me understand that even at that level I was kind of conducting myself at, being part of all these other research opportunities, that there's still more and broader and just more specific research. There's always another level of research you can go on. Reading through on the right, you can kind of understand that a little bit of the sense I was getting at, that as I read through projects 1, 2, 3, 4, that okay, these have, I don't know any of the words within any of these. Kind of starting out, I didn't know what any of this meant, what any of these projects were, and that just kind of helped inspire me to understand that, like, okay, I might be smart, but there's smarter people still. I still have more learning opportunities. I still have things I can do. So with the NSBP Simons Foundation's scholar, my focus was kind of working with LaToya. She's actually one of my desk mates, but my focus was on applying density, well, a multi-layered perceptron to density functional theory. And with the idea behind this is giving these two equations, which is the Hohenberg-Kuhn theorem, kind of as LaToya explained before, we take the many body problem, the many body Schrodinger equation, and kind of convert it to a problem or a variable of density. And that just kind of helps simplify the space we're working in because of how complicated and how multidimensional the many body Schrodinger equation can become. So these two equations just kind of give the direct link to how we can give it to relate it as in terms of density. What they just kind of say is that the true ground state energy, the ground state energy as related to density is greater than or equal to the true ground state energy. And then the second one just says that the truly optimized ground state energy as related to density, so that once you optimize the density, you will get the true ground state energy. And so my goal was just to apply a multi-layer perceptron with the schematic given below to this idea. And so going through the summer, I was kind of building out my repository on how do I use a multi-layer perceptron with its density functional theory, and just kind of combining everything into my project. And so by the end of the summer, I was able to produce these 3 graphs. The first 2 on the left, the top and bottom, is a polynomial function, and then the neural network just assumes a line of best fit without any information. In the bottom is an example of a grayscale image of a handwritten digit. And then at the top, you can see a little bit at the ray, the multi-layer perceptron correctly identifies what number that is without any information about except the values for the pixels. Moving over to the middle 2, this is just the gradient descent method to how quickly they converge to the answer. And gradient descent is one of the methods we use for the multi-layer perceptron, so we can kind of converge to an answer. And then on the right, we have kind of the work I was doing. So the whole point was that we want to use density functional theory to be able to understand quantum objects, quantum molecules that we don't that traditional DFT kind of struggles to model. And so for us, we wanted to do inorganic molecules. And so these are 3 example molecules that we tested on. We trained on 6 and tested on 6, and just 3 examples of it. And so we have in the blue, this is the DFT calculations we did. So this is the benchmark. And then in the orange, this is the predictive value outputted by our multi-layer perceptron. And so this just goes to show that, using this method, that this is multi-layer perceptrons and implementing AI within DFT is actually relevant and is able to give us results that we want. And on the bottom is also just how quickly they converge using the density or gradient descent, stochastic gradient descent. And so by the end of my junior year, I have a internship at the Flatiron Institute in New York City. I'm an IBM HBCU scholar, I inspire student researcher. I went to a JNF caring for democracy, a physics student worker, and a tutor, along with winning the 1st and 5th place in the think tank that Bay Systems hosted locally on my campus. And so junior year for me was a big year just to kind of reaffirm my belief in my ability to conduct research as a physicist and just as a student at a HBCU. And so for me today, kind of incorporating everything, these are some of the my posters, my 3 posters for my 3 internship opportunities, kind of the final posters I presented at going across the country, just sharing the research. Just some of the documents that, kind of for me, just kind of stood out to me. I never thought people would actually want to, support me in a sense, for one reason or another, but just to show that there are people looking out for minority students like myself that want to be engaged and lend a hand within the field. And so me today, as I said before, I'm a physics major at Alabama A&M. I am the chess club president. I'm an IBM HBCU quantum scholar, an Inspire student researcher, an S&P 23 scholar. I'm a part of an NSBP, the PARS program, Society of Physics Students, and continue. And for me today, what this all presents itself is in my resume. Kind of comparing from before my leaving high school to now, I have a lot more to add to my resume. I'm more well-rounded, more experience working as a physicist, and just overall, I feel a lot better about myself compared to freshman year. And opportunities like this is really what helps shape, myself and my future. And I really am appreciative tour experiences like this because this helps build up my repository. And so, kind of closing out, I say I call myself a physicist because even when I gave up, I didn't give up. Through all my 3.5 years, 4 years of college, there's multiple times when I wanted to give up, just quit and say, maybe physics isn't for me. Maybe I have to do something else. Maybe I'm on the wrong path. But even when I gave up those times, even to this day, I still call myself a physicist. I still struggle and do the things that's required to engage. So why I choose quantum research? I choose quantum research because it's who I am. For better or worse, it's who I am. As a physicist, it's the next stage within the research for me. So thank you guys for listening to my story, for being here, for supporting me, and for caring for people like myself that feel like they don't belong, but you guys help us feel like we do belong. And then here are just my references. So thank you guys so much. If there's any questions, I'll be free to take them.
Thank you so much, Cornelius, for that inspiring presentation. I didn't know that you and LaToya were connected at Simon, so that I knew you were both in it, but not at the same time. So that's a very nice coincidence. And so there's going to be some questions. We're a little bit over the hour, but I believe we have some time. If not, Reza can let me know.
Yeah, that's no worries.
Yeah, that's okay. We can go a few minutes over.
Right. So we have one question here from Ibrahim again. So thank you for the question. If you want to develop more in this field, as you mentioned, have you heard of the Coding School's Qubit by Qubit program teaching Circ, or IBM's Quantum Explorers teaching Qiskit, Cornelius. They teach
Yeah,
a lot
so
of computing and coding if you're interested.
it's actually, and that's why, okay, actually, LaToya kind of knows this a little bit, but at times like this, I kind of struggle to keep my excitement in a little bit, so it might leak out a little bit. But actually, yes, so actually, currently, I'm applying to the Waterloo School for Quantum Computing. They have a session over the summer where they're looking to teach students kind of quantum computing. Kind of from my contact with the IBM research or the quantum research, in Thomas Searles, there's been multiple programs that I'm actually applying to right now. So I'm applying to the Waterloo. There's one with Quantanium I'm looking to apply for. I'm also looking to apply for some at Princeton and some at Indiana University. So yeah, really any opportunities to help engage me in quantum computing, I'm always kind of eager and actively looking for. So these are opportunities I am like engaged in to help kind of expand my horizons. So yeah, yes sir, yeah. I haven't heard of those ones specifically, no, but I have heard of similar ones that's kind of related to those ones.
Okay, great. Any other questions can be put in the chat. I had one to get the ball kind of continue rolling. Can you just tell us what is a multi-layer perceptron? Just to clarify that.
Yeah, so basically, a multi-layer perceptron is a way that a machine can learn, essentially. So the way it works is it mimics kind of the neural pathway within the human brain. And so I can go back real quick to kind of show. Okay. And so, yeah, kind of going with the schematic I had, the whole idea is that, right. So the whole idea is that we have an input layer. So the input layer can kind of be, for us in this internship, our inputs consisted of the coordinates, so X, Y, Z positions of the electrons, and then so the X, Y, Z positions of the electrons, and then just kind of a grid to understand like where they were. So kind of simple input layers, but using those inputs, the neural network works by using like weights and biases. So each node gets a specific weight and a specific bias associated with it, and it changes for each hidden layer. So each hidden layer kind of affects the previous one. And then using a method such as gradient descent, we kind of optimize the hidden layers so that they kind of converge to an optimal answer, or one with the least deviance in the derivatives. The complicated subject, I kind of took my whole summer to understand how it works myself, but essentially the way I understand it to work is that it works by using gradient descent to find the answer with the least variance and the derivatives, the partial derivatives of the input layers. So some complicated way of derivatives and input layers works. Sorry if it was a bare bones answer. I'm still not understanding myself.
No, that was great. Any other questions can be put in the chat. I think LaToya, you put a +1. I don't know if that was another question or just voting up Ibrahim's. Okay, just voting up Ibrahim.
Just voting up, yeah.
Okay.
So yeah, any other questions can definitely be put in the chat. Reza, I will get links and information for the National Society of Black Physicists and for the Quantum Noir conference that are coming up. I'll get that to you. So when this is posted in video format, we can have some of those links in the description, perhaps, and people can find out more about these organizations and upcoming opportunities, and just how we highlight Black physicists and reach out to everybody in the community who has the wherewithal to do physics research.
Very good. Thank you. Thank you, Alan, for moderating the Q&A sessions, and thank you, Cornelius and LaToya, for your great presentations. It was great to meet you guys and hear your presentations and all your hard work. Just to close out, I just wanted to mention our next session is going to be it's the second Tuesday of March, which is March 12th. It will be also at 3 p.m. Eastern. Looking forward to your participation. Unless there's any other questions, we can end this presentation. Thank you very much. Thanks for your time.